Dear student, myself Dr. Surekha B. Jaiswal, Head Department of Physics, Boreshwar College, Bhukardan, District Jalna. Today we will see mechanics properties of matter and sound, course code number Phy101, semester first. Now in first chapter we discuss Catter's pendulum, Newton's law of gravitation, gravitational field, gravitational potential and gravitational potential of mass. Now Catter's pendulum, it consists of a metal rod weighted at one end so that center of mass is much nearer to one end and having two fixed or movable knives K1 and K2. This pendulum is used to determine the value of G, that is acceleration due to gravity. Catter's pendulum is a compound pendulum which consists of a brass or steel bar. If metal rod is of uniform cross section, a heavy cylinder is inserted at one end of the rod to shift its center of mass towards this end. Two more adjustable weights, one heavy of metal and other light of wood, are on the rod to make the time period about two knives. See in figure Catter's pendulum. A Catter's pendulum consists of a rigid metal bar having two knife edges K1 and K2. See in figure. That is a metal bar having two knife edges K1 and K2. Now, whose position can be altered along the length of the bar? M1 and M2 are two cylinders of same size and shape. See in figure, that is M1 and that is M2. These two cylinders having same size and shape, and this M1 is made up of wood and while M2 is made up of metal like iron or brass. There is a third adjustable cylinder M3, see in figure, whose position can also be altered along the length of the bar on the outer surface of M3. See in figure, there is an adjustable screw whose position on the surface of M3 can be changed. This helps in the final adjustment of the time period. Now the position of knife edges K1 and K2 are fixed so that they face each other and are on either side of the center of gravity of the pendulum. The time period of the pendulum about each knife edge is determined. In the beginning, the difference in the time period may be large. The position of mass M2 is adjustable suitably so that the difference in time period decreases finally by adjusting the position of the masses M3 and M1. The difference in time period is made extremely small. Now, the period of oscillation of a compound pendulum about a horizontal axis perpendicular to its length and at a distance L1 from its center of mass is given by T1 equal to 2 pi into under root of K2 square upon L1 plus L1 upon G. If the pendulum is inverted and allowed to oscillate about the parallel axis at a distance L2 from the center of mass, the time period T2 is given by T2 equal to 2 pi into under root of K square L2 plus L2 upon G. Now squaring and subtracting equation 2 from 1 we get T1 square L1 minus T2 square L2 equal to 4 pi square upon G. in bracket L1 square minus L2 square. Since T1 and T2 are nearly equal, one can assume that T1 square equal to T2 square plus alpha square and T2 square equal to T2 square minus alpha square. Therefore, 4 pi square upon G equal to T square upon L1 plus L2 plus alpha square upon L1 minus L2. And from this, 4 pi square upon G equal to T1 square plus T2 square upon L1 plus L2 plus T1 square minus T2 square upon L1 minus M2. Now, Newton's law of gravitation. The gravitational force between any two material objects is given by Newton's law of gravitation and is stated as follows. Every particle of matter attracts every other particle of matter with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. See in figure. That figure shows that two particles of masses M1 and M2. See, that is M1 and that mass, another mass is M2, separated by a distance small r. According to Newton's law of gravitation, these particles attract each other with a force whose magnitude is given by the F, that is F is directly proportional to M1 and M2 and inversely proportional to R square. So therefore F equal to minus G M1 M2 upon R square, where G is a gravitational constant equal to 6.673 into 10 raised to minus 11 Newton meter square per kg square. Its dimension can be determined as follows. So G equal to dimension of F into dimension of R square upon dimension of M1 M2. So dimension of force is here given by M1 L1 T raised to minus 2 and dimension of R square is given, that is L square, and dimension of this M1 and M2 are M square. So after simplification, G equal to M minus 1 M raised to minus 1 L cube T raised to minus 2. Now gravitational field. The area round about a body within which its gravitational force of attraction is perceptible is called its gravitational field. The intensity or strength of a gravitational field at a point, it is defined as the force experienced by a unit mass placed at that point in the field. It is also defined as the rate of change of gravitational potential at the point. If m be the mass of gravitational particle, r be the distance from the intensity of gravitational field, then according to Newton's law of gravitation, F is directly proportional to m into m and inversely proportional to r square. So F equal to minus G m upon r square. For unit mass m equal to 1, we get F equal to minus G m upon r square. Now gravitational potential. Let us consider body having its gravitational field around it. Due to the gravitational field, it will be naturally attract any other body B placed at distance. According to Newton's law of gravitation, the force of attraction will increases with decreasing the distance between A and B, and the force of attraction will decreases with increasing the distance between A and B, so that an infinite distance from A it will be 0. If we replace the unit mass by the body B, the potential energy of B will be equal to the product of masses and gravitational potential at that point. Thus, the potential energy of a body at a point in a gravitational field is equal to the product of mass of the body and the gravitational potential at that point. Now, let us the mass M be situated at P, then the force of attraction on the unit mass due to M is given by F is equal to minus M into 1 upon x square into G. Therefore, F equal to minus mg upon x square, where x is the distance of P from O. See in figure that x is the distance between O and P. If the force is directed towards O, then it will move a small distance dx towards O. Then the work done is given by work done equal to force into displacement. So, work done equal to m into g upon x square into dx. So, the work done when it moves from B to A is given by work done equal to integral varying from B to A m into g upon x square into dx. So, work done equal to m and g are constant. So, work done equal to g into m integral of 1 upon x square dx varying from B to A. Therefore, work done equal to minus gm into 1 upon x square limit from B to A is equal to minus gm into 1 upon x square. Now, B having a distance from this O to B, that is a R1. So, taking limit here R1 to R, and after simplification work done equal to minus G into M into 1 upon R minus 1 upon R1. Now, work done from B to A is equal to G into M into 1 upon R1 minus 1 upon R, where R1 and R the distance of B and A from O. This is potential difference between A and B. If B is at infinite distance, then R1 is equal to infinite. Therefore, the potential difference at A is equal to G into M into 1 upon infinity minus 1 upon R. Therefore, V equal to minus M upon R into G. This equation gives the potential difference at point A, and therefore potential difference at infinite difference. Therefore, V equal to 0. Thank you.